All right, so welcome back. We're going to pick up from where we left off last time, which was with the description of randomized quicksort. Let me give you a 2-minute summary of the algorithm itself, and we'll take it from there. So our input is going to be an array of n distinct numbers. The distinctness assumption is just really a matter of convenience between us. We are going to work with that assumption in place, but it's really an easy exercise to extend these ideas to when the array does have duplicate elements in it as well. Now, what we are going to do is pick an element from the array uniformly at random as our choice for the pivot element. And from here, we are going to partition the array into two parts. Let's call that S1 and S2 here. S1 is going to consist of all the elements that are strictly smaller than the pivot, and S2 is going to consist of all the elements that are strictly larger. So notice that because of our distinctness assumption, this is a complete partition of all the elements in the set that we are considering. Now we are going to recursively run randomized quicksort on S1 and S2, and what we are going to get back is nice sorted versions of these subarrays. And we are going to return S1 followed by S2 with the pivot element sandwiched in between, and hopefully it's clear that this is a sorted array. And now what we want to do is analyze this procedure for its expected running time. And to that end, I'm going to begin by establishing some notation. Recall that what we want to do is really try and get our hands on the expected number of comparisons that happen in this algorithm, because it's really the comparisons that are a measure of all the work that's going on here. So let's first of all use S sub I to denote the ith ranked element in the set S, and ranks go from bottom to top. So assuming that S has n elements in it, I'm going to say that S1 is the smallest element and Sn is the largest. So that's our notation here, and I'm going to use the random variable xij to capture whether or not Si and Sj were compared in a given run of the algorithm. So I want to know if the ith ranked element in S was compared with the jth ranked element of S or not in a run of randomized quicksort. So xij is 1 if the comparison happens, and it's 0 otherwise. And notice that we can capture the total amount of work done by simply summing over these xij's. So what I want to do is look at I ranging from 1 to n, and j greater than I, because I really am interested in unordered pairs here. For every pair of elements, I just want to know whether that comparison happened or not. So this is the combined random variable that captures the total number of comparisons. In a run of randomized quicksort, and what we are interested in is of course the expected value of this random variable. Now you can use linearity of expectation to take that expectation inside, so let me rewrite that as follows. So really what we want to understand is the expected value of xij, but notice that xij is basically an indicator random variable taking values 0 or 1 with probability, let's say pij, where pij denotes the probability that I and j, or the ith ranked element in S, gets compared with the jth ranked element in S. So that's what we care about. So this is really going to be, again, I can basically replace the expectation of xij with pij, because that's going to be 1 times pij plus 0 times 1 minus pij, and that basically amounts to pij. Right, so we are interested in the sum of the PIJs, and for this, of course, we now really have to understand what Pij looks like. What is the probability that the ith ranked element in S gets compared with the jth ranked element in S? So I think this is a nice thing to puzzle out a little bit. When do these elements get compared? For what choices of pivots do these elements end up being compared? So feel free to pause here for a moment and think about this for a bit. And that's what we're going to talk about next. We're going to try and figure out the value of Pij. Once we do that, we'll be basically in business. It's just a straightforward computation from there. But conceptually, this is really the key point in the proof. What do you think is the probability that these two elements end up in a comparison in a run of randomized quicksort? So to build some intuition for the computation of Pij, let's actually walk through a run of randomized quicksort on an example. So here's a collection of 7 numbers. Let's say this is our input array, and I'm going to walk through a possible outcome of randomized quicksort by hopefully making some random choices as we go along. So let's say at the very first step, I pick 3 as my pivot element, and I'm going to actually record that here on the side. So 3 is my first choice of pivot. Now the way the array is going to reorganize itself depends slightly on the details of how you implement the partition function. In the interest of simplicity, I'm just going to write down the elements that are less than 3 in the order of their appearance in the array. And similarly, I'm going to write down the numbers that are larger than 3 also in the order of their appearance in the original array. So we have 6, 7, 5, and 4. So those are our recursive sub-instances that we are going to drill down further on. So let's say that for the array that we called S1, which consists of the elements 1 and 2, we pick 2 as the pivot. And on the other hand, for S2, which consists of the elements 6, 7, 5, and 4, let's say that we pick 5 as our pivot. Okay, so what we are going to see from here is going to be, well, just 1 and 2. That was our pivot here. And then we have 3. And here we are going to have, well, first 4. And then we are going to see 5, followed by 6 and 7. And let me record these choices as well. So on the left hand side, we picked 2 as the pivot, and on the right hand side, we picked 5. And now from 2 onwards, we don't have a choice really. It's an array that has just one element. Similarly, on the left hand branch from 5, we don't have a choice as far as picking a pivot is concerned. And of course, for 2, the right hand branch is simply empty, so we kind of stop here. But on the left hand side, the de facto choice of pivot is going to be 1. And as far as 5 is concerned, it's going to get a default pivot of 4 on the left. And on the right, well, we could imagine that we pick either 6 or 7. The final array is going to be the same because we coincidentally already have it in sorted order already at this stage, so I'm not going to be writing it down again. But let's just say that for the sake of completeness, choice of pivot here happened to be 7. And then on the left hand side, we didn't really have a choice here. That was 6. And this is of course empty. We don't have anything to recurse further on. And of course, everything else is empty as well. So there's nothing further to be done at the nodes that have arrays of length 1. So this is one way of looking at the recursion tree, by just labeling all the nodes by the choices of pivot. And observe that if you were to do a in-order traversal of this tree here, then you actually get the final sorted output. That's really what quicksort is. It's the in-order traversal of the recorded pivots as we go along this recursion tree. But what I would be interested in now is actually not the in-order traversal, but the level order traversal, which is just visiting all the layers of this recursion tree left to right. Unfortunately, The figure that I have here is not nicely drawn, so the levels are going to look a bit awkward, but hopefully you can still make them out. So at the top we have 3, and at the next level we have 2 and 5. So at each level I'm going to read off the pivots from left to right. At the third layer we have 1, 4 and 7, and at the final layer we have 6. And this is essentially the order in which we discover our pivots, and that's what causes sort of all the reorganizing. And remember, the question that we are trying to address is, what are the chances that the ith ranked element gets compared with the jth ranked element? That was the question that we started off with. And I claim that this ordering here is of interest in helping us answer that question. So notice that every run of randomized quicksort leads to an ordering like this. If you just write down the level order of the recurrence tree, which is labeled with the pivot choices, that's going to give you a permutation of the input elements, right? And so you can really think of the sample space as being a collection of these permutations. And if we want to know, so for instance, let me write out the sorted order of the input just for our reference here. So what we are looking at really is 1, 2, 3, 4, 5, 6 and 7. That was our input. And let's say I want to understand what are the odds that 2 is compared with 6. When does that happen? Well, if you think about it, when does 2 get compared with 6? That happens when either 2 is chosen as a pivot or 6 is chosen as a pivot before any of 3, 4 and 5 are chosen as pivots, right? In other words, if 3, 4 or 5, any of those elements are chosen as pivots before 2 or 6 have a chance to come through as a pivot element, well then any of those 3, 4 or 5 will essentially split 2 and 6 into 2 separate universes, right? So for instance, we actually happened to choose 3 as our first pivot, and what that did was that it threw 2 and 6 into 2 disjoint recursive subinstances. So 2 and 6 never face off each other again. And this is true about randomized quicksort and quicksort in general, that if you have elements in S1 and S2, then they never get compared from there, because they're going into these parallel universes and they're going to be minding their own businesses. They're separated by the pivot in question. So when I want to know if the ith ranked element and the jth ranked elements are compared, what I'm really interested in is knowing if any of the elements that sit between the ith and jth ranked elements, do any of them show up as pivots before either the elements themselves, the elements we are interested in, have a chance to show up as a pivot. Okay, so if 2 or 6, either of them, beat the middle elements to the race of being chosen as a pivot, then they will actually engage in a comparison, because then notice that if 2 was chosen as a pivot before any of 3, 4, 5 and 6 were chosen as pivots, then well 2 is going to get compared with 6. In fact, 2 and 6 are going to have an ancestor-descendant relationship in this tree. And the reason 6 is still available for comparison when 2 is chosen as a pivot is because they really had no chance of a separation. All the pivots that have been chosen so far are either smaller than 2 or bigger than 6. So they're still stuck in the same sub-instance. This is of course assuming that none of these fellows here in the middle have been chosen as pivots so far. Okay, so this is really the key observation that drives this whole argument. The key observation is that the ith ranked element and the jth ranked element are compared in a run of quicksort if and only if at least one of them is chosen as a pivot before any of the others in that range are chosen themselves. So here, for example, we have a collection of we have a collection of 5 elements here. Okay, so now these 5 elements, the question is, how do they show up in this permutation here? And now notice that because all of our pivot choices are basically made uniformly at random, each of these permutations are equally likely to show up, and in particular, both 2 and 6 have as good a chance of being the first chosen pivot in this range of elements as any of the other elements do, right? So basically what we are interested in is the event of the first chosen pivot from the elements in this range. So let me write this out. Remember that we are looking at the original sorted list of elements for the sake of analysis, and we are looking at the ith ranked element and the jth ranked element. I've been assuming that I is less than j here, and we are trying to understand what are the chances that these guys are actually compared in this run of quicksort. And my claim is that this really hinges on which element is chosen as the first pivot among all the elements in this range. That's all that we care about. So in a random permutation, basically we are interested in, well, what was the first time that somebody in the blue region made it as a pivot, and the chances that this element made it is the same as the chances that this element made it. The chances are really uniformly spread over all of these elements, because that's just the nature of the algorithm. Pivots are chosen at all points in a fashion that's uniformly at random, right? So you take your run of quicksort and really associate it with this permutation, which is the level order visit of the recursion tree that we just drew. And now in this permutation, I want to mark out the first occurrence of an element from this range, whatever that might be. And the question that we are interested in is this element one of Si or Sj, or is it not? If it is one of those two elements, then I know for sure that Si and Sj are going to get compared, because all the pivots that have been chosen prior to this marked element, these pivots were all either to the left of Si or to the right of Sj, as in they were either ranked lower than Si or higher than Sj, because that's just by definition. The marked element is the first element in this permutation from the blue range, so everything that came before was certainly out of this range. But notice that if you're picking pivots that are either smaller than Si or larger than Sj, then you don't separate Si and Sj, right? A pivot that is bigger than Sj, something from here, will throw the entire blue range into the left recursion instance, and anything that is chosen from out here will throw the entire blue range to the right hand recursive subinstance, right? So a real chance of separation only shows up when you pick a pivot from something in the middle. But if you actually pick one of the extreme ends, Si or Sj, then you do end up comparing Si and Sj with each other, right? So that's our point, that Si and Sj have not been separated yet, and if you pick one of them, then they get compared with each other. But if you pick something from in between, then we have a separation event. Si and Sj get thrown into different parallel universes and then never compared again from here. So the event of interest, really, Pij, boils down to what is the chance that the first chosen element from the blue range is one of Si or Sj. But notice that since we are always picking pivots uniformly at random, any one of these blue elements in the range have an equal chance of making it as the first element in this permutation, in this run of quicksort. So essentially, Pij is going to be 2 over j minus I plus 1. J minus I plus 1 is essentially the number of elements in that blue region. And we have 2 because either the choice of Si or the choice of Sj will work for causing that comparison. Anything in the middle, of course, will cause the separation. So that's our argument for the value of Pij, and now it's just a matter of summing over all Pij's to see what we get. Okay, so let's go ahead and plug this back in to the double sum that we had earlier. So remember what we had was that the expected number of comparisons being made is, well, we just go over all unordered pairs here. So that's I ranging from 1 to n and all j greater than I. And we're interested in Pij, but we now know Pij to be 2 over j minus I plus 1. Now to simplify this expression a bit, let's introduce a change of variables. So let's denote j minus I plus 1 by k, and notice that j ranges from I plus 1 to n, so j minus I ranges from 1, and j minus I is k minus 1, so the lower bound for k is going to be 2, and of course we have j equals n, and j is k plus I minus 1, so the upper bound for k is going to be n minus I plus 1. So k ranges between 2 and n minus I plus 1. To keep things simple, I'm just going to throw in an upper bound here and allow k to range from 1 to n. That's just going to make my life a little bit simpler here. So we go k from 1 to n, 2 over k, and in fact, just so that the summation looks familiar, let me pull out the 2 here, and you might recognize the sum of 1 over k, k going from 1 to n, as something that you might recognize as being the nth harmonic number. So I'm going to rewrite this as hn. So what we have is twice I ranging from 1 to n hn, so that's just n occurrences of the nth harmonic number, so 2n hn, and hn is well approximated by the natural log of n, which gives us an upper bound of n log n out here. So this is just, of course, ignoring constants and so on. But that's the final word on the analysis of the expected number of comparisons for randomized quicksort. And an interesting question that I would leave you with is for you to think about the random permutation that we got induced by the level order. So we said that we'll sort of look at this permutation, and if you consider the permutations as coming out of this randomized quicksort procedure, one thing worth thinking about is, well, is that collection of permutations uniformly distributed over the space of all permutations of the input elements? That's a nice exercise to think about, and one that I will leave you with. So I hope you had fun going over this really classical example of a randomized algorithm. It's a classic, but it's also a very powerful illustration of how randomization can really help. So we're going to wrap up this discussion here. And the next thing we're going to talk about is, again, a familiar problem and a familiar method, but now we're going to inject some randomization. So we've already met set cover, and we've already seen LP formulations for problems, but what we are going to see is actually randomized rounding method for the set cover LP. So that's what's up next, and we'll stop here with randomized quicksort.